Hello, everyone. Thank you for joining us here today. I hope these uncertain times find you happy and healthy. My name is Mercedes Thompson.
And my name is Olivia Caplow-Munro. We do research under Professor Jessica Kaywork, and we are part of a team called the Work Squad. Our name stands for Student Quasar Absorption Diagnosticians. Our goals with this research is to find out more about the gas dynamics, metallicity abundances, and other properties of the CGM around galaxies. We are curious in understanding how different gas dynamics play a role in the evolution of galaxies.
Though picturesque and beautiful, galaxies are not static objects. In fact, they are cannibals, as larger galaxies will gravitationally strip smaller galaxies in order to replenish their own gaseous supply. As their stellar inhabitants grow old and end their lives in violent explosions called supernovae, they pollute their host galaxy with metals. And the supermassive black hole found at the center of galaxies accretes and fuels near relativistic jets out encasing the galaxy in a halo of gas, also called the circumgalactic medium. Together, these processes make up the cosmic baryon cycle, where a baryon is just ordinary matter, anything that we would see around us now. But where are these baryons? When you look at this, the luminous inhabitants of a galaxy, its mass does not account for the total mass that we find in most galaxies. Our theory, it is most likely found within the CGM.
We exploit a few characteristics of light to find out more about this diffuse halo of gas around galaxies. As you can see, we're following the sight line of a quasar, and as it passes through a galaxy halo, we see absorption features come down onto our spectrum. As the light continues to travel to space through space to our telescope, these lines become redshifted. And it's our job to decipher the information that we get from the spectra that we're looking at. We get our spectra from the Hubble Space Telescope, and the Work Squad's job is to identify all of the absorption features in our spectrum. We're curious to find places where we have absorption systems, places where we have both hydrogen absorption and absorption of other metals, metals being anything that's not hydrogen or helium. We want to find systems like this where we see absorptions at the same redshift, because this indicates that the light from the quasar is passing through a halo associated with some galaxy between the quasar and our telescope. The Work Squad has created a trusty cookbook so we can comb through all of these spectra looking for these systems. Over the past few years, Work Squad has identified every absorption system in over 230 different spectra from the Hubble Spectrographic Legacy Archive.
To complement this UV spectroscopy, we use two other telescopes called the Gemini North and South telescopes to collect optical spectroscopy in order to characterize the galaxy itself. Using the Gemini telescopes, we have gathered over 3,000 galaxy spectra at a redshift about 1, and that is more than 300 targets per sightline to the quasar itself. This is one such spectra. You can see that it has a very obvious continuum, this sort of bow-like feature in the graph. And from that bow, you can see the different spikes are emission from the galaxy itself. And this larger kind of chunk that looks taken out, though not absorption from the actual galaxy, it's called telluric absorption from our own environment. However, that is what an absorption feature would look like. And using these and a program called Red Rocks, Work Squad has gone through and we have classified by hand all 3,000 spectra as either star-forming, elliptical, or star-forming and elliptical. And we make this classification based on the types of lines we see. If it's largely emission lines, we can determine that active star formation is going on because we can infer that there's some sort of fuel source, i.e. a star, that is supplying the energy for this gas to radiate. It's kind of, every element has a very specific energy that it will absorb, like its own key to a lock, that will cause it to radiate a very specific barcode unique to that element. And by examining these spectra and being able to pick out the patterns of which barcodes we're looking for, we can determine what metal or what elements are currently at the galaxy itself. In our survey is called the CGM squared, which is the Cos-Gemini mapping of the circumgalactic medium. And in our survey right now, we are specifically interested in emission galaxies or star formation galaxies. And the lines that we look for to classify these galaxies are hydrogen alpha, which you can see here on a close-up on that same spectra on the leftmost panel, and then on the right, H beta as well as metals. And we look for these things because it indicates that there's enough material being actively cycled in the baryon cycle of the galaxy to produce new stars. Metal content is generally linked to some kind of remnant of old generations of stars who have already gone supernova and polluted the environment, which therefore just makes more material for even more stars to form. We can determine this redshift because we know here on Earth where this emission would take place, and by comparing the observed wavelength to the wavelength, or to the known wavelength here of that emission, we can determine what the galactic redshift is.
Never mind the blue angels flying by my window. So putting all of the things together that we have high definition galaxy redshift, we have redshifts for absorption systems from our quasar spectrum, and now we can start the matching process. So in the picture on the left, you can see in the center part of the picture, we have our quasar and we have a couple of galaxies kind of speckled around the sight line. And you can see their redshifts, and then in the spectrum of the quasar on the right, you can see absorption systems that we've identified at particular redshifts, and those redshifts match those of the galaxies nearby our sight line. And this is super exciting because what this means is that we're starting to get little pinpricks into the CGMs around galaxies. And from that, we can start to build a map of what is going on there. We can build a map of the different species of gas that are in the halo. We can find out about the dynamics and the velocities of this gas as well, and start building a connection between the types of elements that we see in the halo and how that might be connected to the overall evolution of the galaxy itself.
Exactly. Together, these two different types of observation allow us to create a holistic view of the galaxy itself, and gives us a window into the cosmic baryon cycle that dictates a galaxy's evolution. It's through these measurements of these emission lines and these absorption lines that we begin to make different kinds of conclusions. We can determine the mass of a galaxy, its star formation rate, its metallicity, the metallicity of its CGM, and this allows us to begin to connect these different aspects of a galaxy itself. It's interesting to note that to date, no correlation between galactic metallicity and the CGM metallicity exists. And it's our hope that through our work, we'll be able to find this connection and fill in the picture of how a galaxy evolves. We would like to thank everyone that helped us get here. It's been an amazing journey, both personally and together. We would like to thank Professor Jessica Work, as well as our other mentors, Matt, Kirill, Hannah, Grace, and of course, all present and past members of the work squad and future members of the work squad. Thank you guys.